sorted by popularity or the ranking models. So sorting is not like alphabetical sorting. We need to return it by the popularity, or mostly looks at that we are looking for the popularity. Yes, Abdul Rahman.
अस्सलाम वालेकुम मैम।
Yes, Walaikum
अ,
Salam.
मैम मैंने मीटिंग लाइव कर दी है, तो अब मैं रिकॉर्डिंग स्टॉप कर।
Yeah, sure.
ओके, यू कैन कंटिन्यू।
Okay. All right. Next thing is that we want it to be scalable, like the system should handle high traffic volume, and the system should be highly available. Highly available means like whenever any part of the system or some parts of the system are down, our system should still be available to return results, right? Um, Next thing is that we have clarified the requirements, we have established the design scope. Next thing is that we need to discuss the back of the envelope estimation. Like we need to estimate how many requests per second we will be sending, how much storage we will be needing daily, right? So we can assume, we just discussed that we have 10 million daily active users who are searching, right, on daily basis. And we assume that one person performs on average 1% performs 10 searches per day. Although this is very small, like probably users search a lot. Although these days these days mostly people are doing things on GPT, so these have reduced a lot. But when there was not GPT, then definitely there were a lot of searches that were being performed every single day on these search systems. So we can assume that there are 10 searches per day and 20 bytes of data per query string. This is like one query string can have how much data, like the search query that we are typing. So we can assume that this is like there is some limit, like because we can definitely in Google we can just make it as long as we want. Like it can be very long, but for our system we assume that this is limited, like the search query is limited to 20 bytes, right? And then we assume that we use ASCII characters because we discussed this in the requirements that it needs to be ASCII characters encoding, and in that case, like it's one character is equals to 1 byte. So based on this, if we assume that the query contains maximum 4 words and each word maximum contains 5 characters, like so in that case we will have 20 bytes per query. Okay, next thing is like when we enter the character into the search box, right? So what happens at the backend is that the client will send the request to the backend for autocomplete suggestions. So when I search, because let's suppose I have to search for this query dinner, right? So when I search for, when I type Q in the search box, this query will be sent to the backend, like an API. It can be an API, right? REST API. Then when I append I, then another search query will be sent. When I append N, another search query will be sent, and so on. But when I continue typing more characters, a new search query will be sent for each new character I type, and then it will return the top K most frequent search queries from the database. Okay, next thing is like how many queries per second we will have. We assume that we have 10 million daily active users, and each user on average makes 10 queries per day. 10 queries. So because we have daily active users, so we multiply, like these many queries we will have per day. And then we know that the maximum query string length is 20 bytes, which is like 20 characters, because one character is equals to 1 byte. And we have to calculate it for per second. So we divide it by the number of hours and seconds in one day. So we get 24,000 queries per second. So this is what our system will have. Like we'll have 24,000 queries per second. On peak, we can say that the load might be double. So we can have 48,000 queries per second. These might be on some day, for example, there is Black Friday or something, when some specific days when users are searching for some more popular things, or more users are searching. So in that case we can have peak queries as well. And then we can assume that we have 20% of the daily queries are new, because it's not necessary that users are searching new things every single day, because a lot of users might be searching. Multiple users might be searching similar queries. For example, 80% of users might have been searching similar things. So we can say that 20% of the daily queries are new. So in that case, since we have 10 million active users, 10 queries per day, and 20 byte per query, so we can just multiply it with 20%. So these were the total number of bytes we needed for all of the search queries. And since we know that only 20% of the queries are new, so we only need 0.4 GB of new data that needs to be added to the storage on daily basis. Okay, because we do not need to add the data that is being like that is already stored, since we know only 20% is new, so we need to store only that one, right? And next thing is, so we have discussed the requirements and high level requirements, and we have discussed the requirements and the problem. So scope and problem and the back of envelope estimation. Next thing is that we need to discuss the high level design. So for this thing, like we discussed, like we want to have two services. One is the data gathering service, and other is the query service. What data gathering service will do is will gather the user input as users type the queries. So these are the input queries that it will gather, and then it will aggregate them in real time. So we know we will later discuss that real time is not practical for very large data sets. So, but there are some other options for as well to aggregate the data. We will discuss that in the deep dive. And so data gathering service simply gathers the user input queries, and then it will aggregate. So to count the frequencies, like how many times that specific query was being searched. And next thing is the query service. So this is like when you search for a query, you will have to return 5 most top K frequently searched terms. So query service will return these search terms. Now, what the data gathering service does. So for data gathering services, we are aggregating the data for queries being searched. So we have like one frequency table, which will store the frequency of the query. So let's suppose the user searches these queries: Twitch, Twitter, and then Twilio. So once when the user searches initially, your table will be empty. When user searches for Twitch, it will increment the frequency to 1. It will search for Twitter, increment frequency for 1. Again, it searches for Twitter, it will be incremented to 2. And this is how your frequency table is built. So data gathering service is simply like storing the frequency of these search terms that are being searched. Next thing is the query service. So it will store the query string, right? And like we already knew that the data gathering service built this frequency table. So we have, let's suppose, this frequency table where Twitter is being searched 35 times, Twitch is being searched 29 times, and Twitch Prime is searched 18 times, and so on. So when the user will start typing start typing in the search query. So let's suppose user types TW in the search box. So this query service will return the top K frequent. So you can see that TW with TW Twitter is matching, Twitch matching, Twilight. Like all of these are being matched with TW in the frequency table. So based on this, it will return only the top 5 because we are returning the top 5 results. So top 5 results will be Twitter, Twitch, Twilight. Okay, it's actually sorted by frequency. So it will return these 5 results. So you can see it has returned these 5 results from the table. Next thing is like is the so here we are also discussing, like, we are getting the results based on the frequency, but we might also return based on popularity and some other terms as well. So in real systems, like, your results are being ranked based on some other factors as well, like frequency is not the only thing. But in this design, we're discussing that we are doing this based on the frequency. So to get the 5 most recent, 5 recurrently searched queries, you will execute this SQL query on the database. You say, okay, select all of the rows from frequency table, where query will have this prefix and order by the frequency, return the 5 most queries. But definitely this will be acceptable solution when your data is small, but in the real systems like in Google search and other Twitter or other places, like it can be data becomes very large. In that case, like using these like using these SQL queries on the tables becomes a major bottleneck, right? Because the data is very, like, you have a lot of data stored in your tables. So we will discuss like how we can make optimizations to our system to make to return to have fast response time. So in the design deep dive, we will discuss this trie data structure. We will discuss what is a trie data structure. So, and what is data gathering service, query service, how we can scale the storage, and what are the trie operations. So first thing is the trie data structures. I'm not sure if you guys have already heard about this, but this is something like trie data structure is like a tree, and it is actually abbreviated from retrieval. So which means that we are trying to retrieve the strings, right? This is actually for string retrieval operations. So what is a trie data structure? It looks like a tree. So if you look at this, it looks like a tree, but it stores the strings prefixes so that you can efficiently search for substrings from the string prefixes, like, sorry, not substrings. You can efficiently search for strings prefixes from the trie in with faster response time. So like if you look at how we can build a trie, so trie can be built like it is built using a using hash map as well. But what you do is usually what you usually do is like you have a root which is just the start of the tree, right? And then you store 25 26 like it is not necessary that you have 26 alphabets. If you have special characters or other integers as well, you will probably store those as well. But for now, let's say that we have 26 alphabet characters, right? So each node will have like 26 each node will have 26 characters stored. So this is your root node. So root node will have 26 characters, like it will have A, B, C, D, and this on W and this on Z. So it will have these 26 children, right? So root node has 26 children because we have 26 characters, and each will store the character, relevant character, right? If you have like, so when you move to the next node, so it will again have 26, like it will again have 26, this node will have again 26 children, this node will again have 26 children, and so on again. Then you will go to this node, it will have 26 children, 26 children each node, like this. So how we build how we build a trie using the strings. So let's suppose we have like these queries being searched, and we need to construct the trie data structure. So what we do is first we have this root node, and then we have its 26 children. So we know that A is not there, so probably A is empty, right? B node is also empty. These nodes will be initially empty, like not like this, like this. So A node is empty, B node is empty, C node is empty, and so on. But you have like T here, right? One way we can do is like what we can do here is that we can just use a hash map, right? So we know that we have this root node, and this root node can store a hash map. So in hash map, whenever we get a character, we just create a child node that with that key T, right? And if we have R here, then sorry, it's like this. And if we have something that starts with a different character, definitely. So we have here it's starting with T, and this is something that is starting with different characters. So we will have another hash entry with W. So since we do not have A or yes, Safant.
मैम हैश मैप में तो हमारे पास की और वैल्यूज होती हैं।
Hmm.
ऐसे ही होता है ना?
हम्म,
क्योंकि ये जो अब आज वो जो डिस्कशन हो रही है, इट्स जस्ट लाइक बी ट्री
हम्म.
डाटा स्ट्रक्चर, ऐसे ही है ना?
No, no, this is not B tree. This is trie data structure.
इट्स लाइक दैट।
Yeah.
उसी तरह उसकी तरह ही जो है ना ये, और लेकिन हैश मैप के अंदर तो कीज होती हैं और वैल्यूज होती हैं।
Yeah. So what we are doing here is like
जी।
we know that here we have the root, and this root has 26, can have maximum 26 children, right? So instead of storing that as you can either store this as a vector, like for example, as an array of 26 characters where A is empty, B is empty, and whenever you have to store something, T will be stored in its own spot, right? Or other way you can do is like you can use a hash map. You do not need to have these empty spots. Although this will not make any difference, you can just have, okay, I have like this root node, and uh, this root node has character T, character R. These are its children, right? Sorry, character W, and so on. So then when you come to the next node, which is T, so you know that this node has characters again T, sorry, not T, R, and O, right? And when you come to uh, this R character, R node, then R node has uh, E, U, and Y, right? Like this. So although it has like this diagram like represents it's like this, but in real trie structure, this initial character definitely you do not need to store, right? You just need to store the new character that is being added, because you can then traverse from here. You know that you need to search for tree. So you will start from T, then you will go to R, then you will go to E, and then you will go to next E, like this. So the trie data structure is like, so now you have to store these search terms in your trie data structure, right? So what you do is like you have this root, where a root node, and then in root node you have these two nodes, because one node is uh, like this. You know that T is being started, like there are four T's, right? Um, in fact, let's just see how we can insert the word tree in our trie data structure. Initially, let's suppose our root was empty, right? So we have this empty root. We start with this. We first store T. This is the first node. Next character is R. So we say, okay, let's just store R. Next character is E. We create a new child of the R and store E. Next character is you create a new child of E, and then we store E. And this is the end. So whenever you reach the end of the whenever you reach the end of the string, you just store something, a boolean, like this is end of string set to true. You can just set something like this. So whenever you are searching for something for a value tree, and when you reach the node which has this being set to true, then you will know that this is a complete uh, like this is a complete word. And if you are, for example, searching for prefixes, again this is easy. So if, for example, we are searching for tr, then you know that tr is, this is the prefix that we are searching for. And prefix is when you have this end of string set to false, you know that that is your prefix. Next thing you need to store is trie. You have already stored tree, and next thing you need to store is trie. So for trie, you started from root again, and then you see that T is already present, right? T is already present in the child of this root node, so you do not need to store it as a separate. You do not need to store it as a separate node. You will keep it there, and then you will say, okay, next thing is R. So R, you go to the child of T, because you have to move like this T R, like so. So you see that R is already there, so you do not need to store this. Next thing is Y. So Y is so as the child of Y, you search if Y is there, and the child of this R, so it is not there. So you create a new node and you store Y here, and then you mark this as true, like end of string is true. Next, you have TRUY, TRUE. So you already have T, you already have R, then you do not have U, so you store U here. And then you have E, so E will go after this, and then this will be set to true. Then you have toy, so you have T already here. O is not in this, so you store O and then you store Y. Finally, you have wish. Now, wish, you start from the root. W is not there, so you start like this W, and then you continue building your try like this. So once your try is being built, now you can perform the queries operations on this try data structure. And how efficient this will be, let's just discuss this. You can search for prefixes, you can search for whole words. So when you will be searching for something like TR, so when you are searching for TR, then you know that you have to look in this subtree. So when user typed TR in the search bar, right? So you know that you need to search in this subtree. You do not need to worry about the remaining subtrees, right? So in that case, you just traverse this subtree, and then you are here, right? And then you traverse this whole subtree to reach the end of the words. You know, you will reach when you have the end value set to true, and then you will know that these are the end of and those words as the suggested terms in your search query. Okay, but the thing is that this is just the basic try structure. We haven't yet stored the frequencies because we need to return the top k frequent element. Right? So for that purpose, we also store the frequencies in our try data structure. So let's suppose we have this query, this frequency table. So what we do is, like, when we reach the end of the words, so instead of storing the end Boolean to say that this is the end of the word, we just store the frequencies. Like if try is being searched 29 times, then we store the frequency for try like this. We just store the frequencies here on the leaf nodes with and words are ending. So now how this autocomplete work with the try. So let's suppose we are searching for a prefix. So let's suppose we are searching for TR, and like we already discussed like how we will before going to like let's so we discussed like how when we are searching for TR, so we are here and then we will like do the traversal on this subtree, and then we will return the top k frequent elements from this. So let's suppose if we are looking for top 2 elements with frequency TR. So here we have these 3 nodes that are being returned, and top 2 from them, these are this true and try. So these will be returned to the user, and tree will not return to the user. So now what is the time complexity of this operation, search operation on try? So we are searching for a prefix of length P, and there are total number of nodes in the trier, and these are the number of nodes. So in this case, we have like how many number of nodes we have in this case? Like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like we have 14 or 15 number of nodes. So these are the number of nodes that we will have in the try, and number of children of a given node. Let's see, this is C is equals to the number of children in a given node. So when you have to search for top case searched queries, first thing we need to do is that we need to search for that prefix, right? So if you are searching for the prefix, that is going to take O of P time, right? Because you have to search for TR. So you go to this node, this is one step, then you go to this node TR, this is second step. If the length is like, for example, 100 for a prefix, then you will be searching, you will have to go through traverse the 100 nodes. But in this case it was 2, so you have traversed 2 nodes, so it's taking O of P time, right? So this takes O of P time to search for the prefix, and then next thing is you have to traverse this subtree from prefix node to get all valid children. So once you have reached the prefix, then you have to search its subtree, right? So to get all of these values. So so this will take O of C time, because we know that there are C number of children for a given node. So so we have to like traverse all of those children of the given node, and it's not necessary that it's going to end here. So and each node has some further children. So We say that number of children, not exactly the exact descendants of these children, but actually all of the children of that subtree. Or we can simply say that C is the length of this number of nodes in the subtree. So this is going to take off C time to search for all of the words within that subtree. And next thing is the that we have to, once we have searched for these nodes, then we have to sort these children based on the frequency. Sorting usually takes O(n) log n. So in this case, we assume that C is the total number of nodes. So this will be, instead of we can say n log n, we say this is C log C. So total time that we will need to search for top k frequent words from this tri-data structure is C log C, because we have like O of P time plus O of C time plus C log C, and because C log C is the dominant term here, so we say that this is the time complexity step for searching. Sorry. Okay, next thing is like all right. We already discussed like how I will be searching for this tree, and so we return top 2 from here, and we also discussed the time complexity. It's like or C log C. Now, this is also, again, this time complexity is still not good enough for a real time or very fast response system. So how we can improve this, right? So what we do in this case is that because in this case, what you have to do is it will become slow because you will need to traverse the entire try. In worst case, you will probably have to traverse the entire try. In worst case scenario, what could that be? Like if you are searching for T and you're searching, this is the first search word that you sent to your try. So you are in worst case scenario almost traversing a full try, right? So to only get the top k search results. So how you can improve the results? What you can do is that first thing you can do is you can limit the maximum length of a prefix. So sorry, where is that? Okay. So you can limit the maximum length of a prefix. You can say, okay, user, like when we are searching for prefixes, we do not want to search for characters beyond 50. So if user enters a search query which is above 50, that has the length of above 50, then you are only searching till length character 50, or do not care about the remaining characters. So you limit the maximum length of the prefix, and you also cache your top search queries at each node, so that whenever you have to search for something, would you cache? We will just discuss this later. So, so what you do in the top, how you cache the top search queries in your try. So what you do is, like if you have this try example, right? So here what you will do is like so if you're here on the top node B, and if the search terms beginning with B are being searched by a user first, so initially something that was being searched with the character B. So you will, once you have traversed the whole try to search to get the top k frequent queries, starting with B, you will just store these on this node. So next time when something that is being searched again with B, you do not need to traverse the try again. You have already cached the results here, so you can just immediately return the results to the user. So what you do in this case, that on every single node, you just store the results like top k frequent queries on every single node. So in this case, this is something that is starting with BE. You store all of the results starting with BE. Here you store all of these results starting with BEE, and so on. But one of the problem with this is like this will definitely increase the storage size a lot, because you are storing on every single node, you are storing these top k frequent search terms. So this is definitely going to make your storage you need a lot of storage to do that. But I think whenever you are making these kind of whenever, sorry, I just, just. Okay, so we have like let us revisit the time complexity after applying this. Okay, so now we know that we have stored this, but the thing is that whenever you are making something that you need to make fast, you have to make trade-offs. Like you need to use more storage usually. Like data structures के आपने मतलब courses अगर आपने lead code वगैरह भी किया हो. So whenever you are building some algorithm that requires to return that requires less time complexity, then you need to use more storage. That is a trade-off that you need. Because we are looking for faster results, we do not care about storage here, so it's okay to store the results here to return the faster results. So prefix node, we find the prefix node, to find the prefix node, the time complexity is O1, right? Why it is O1? Because we have already stored the results here. So whenever you are searching for something that is starting with B, so this is just going to return immediately. The result is being returned immediately. And if you have to return the top K elements, again, this is being returned in, like this is again being returned in O1 time. So so based on this, like we using this storage mode, we have reduced our time complexity from O log C, C log C to O1 to fetch these top K queries. Okay, so this is one of the optimization we made. Next thing is the data gathering service. So data gathering service is like we saw that we need to update the data in whenever user will type the search query, right? We need to update the data in real time. But this is something that is not practical because the thing is that whenever you are typing, so when user were initially, we were looking at that user's search for tree, try, like this was the example that we were looking for, right? Where is it? So we were looking for this example. The user searched for user was where are those? So yeah, this one. So like we had these 5 words: tree, true, try, toy, which, wish, and win. So when user like search these queries, we just keep like we need to update our try on like whenever you are user initially when the try is empty, definitely then we have to store the results in the try. So when there was nothing in the try, we saw that how try was being built. And whenever a new word, for example, this is in your initial try and there is a new word that is being searched, maybe let's look let's make a let's just think about true, tree is already there. Trust, let's suppose user search for trust, right? TRUST. So this is a new word that needs to be inserted into the try because it's not already there, which means you need to update your try. So you need to update your try, and if you are doing something like naively, like you are updating whenever user are searching new words that are not in the try, and you are doing this naively, that you are saying, okay, every time any user enters a new word, I have to update my try. That is actually going to create a big bottleneck because there are a lot of users that are searching every single second. Like you saw that there are 24,000 queries per second, so you are every second you are making 24,000 updates to your try, which is not a good which is not for real time updates, right? So this will not make your updates real time. So how can you avoid this? How can you optimize this? So for this, what you do is like instead of updating your try real time, you just update this infrequently. For example, you can say I can update my try once per week, or I can update if it needs to be really fast. And like if it's like a lot of, if I have a lot of new queries, I have to return the latest results. For example, on Twitter, I have to return the latest results every day. So in that case, maybe I can say I can update my query every 5 hours or like this. So it depends on your use case. So for example, if this case, let's suppose we want to update our try every week, like once per week. So so we saw that users may enter billions of queries per day, and updating the try on every query will significantly slow down your query service. So one more thing is like your top suggestions may not change once your try is built, so you do not need to update your try frequently. So how you can design a scalable data gathering service. Okay, so what you do is like you have an analytics log. So whenever users are searching for something, you just store those in analytics logs. Analytics log is something like you have a query that is coming from the user and at which timestamp that query was coming. You just make it an append only log. So you do not care about like how you have to like sort this. You just, whenever a new query comes, you just append it to your query log with that timestamp. So at 1st October 2019, tree was searched at this time, you just append this to your query log. And then try was being searched, tree was again searched at this time, you just appended it. Here you can see that you haven't updated the frequency in the log, you just append it. So this is what you do in your analytics log. You just keep your queries with timestamps in your analytics log. Once your analytics log is built, then you just use aggregators. These can be some APIs, right? Written with backend codes. These are aggregators that will aggregate your logs from the analytics. These will fetch the logs from the analytics logs, and then these will aggregate the data based on. So let's suppose you are trying to store the frequency of. You're trying to aggregate the data on weekly. Based on 1 week. So you can say like I need to aggregate the data how many times tree was being searched in 1 week, right? So you would just aggregate based on this timestamp and based on this query. Here you can here you can see that 1st October, 2nd October, all of this is coming in within 1 week. Let's look at another example like how this will be stored in aggregated data. So when you look at this, you can see that this tree was being searched on starting on 1st October. It was searched 12,000 times. So this was for 1 week. Then new week started at 8 October. So you are not storing this within this one. You are just storing with this timestamp that on next week it was being searched 15,000 times. On next week it was searched on 9,000 times and so on. So this is how your aggregated data will look like. So aggregators will aggregate your data based on your weekly schedule, based on your schedule, like how many times you need to store it. So this is what aggregators store, and then that aggregated data will be stored in your database. This is being stored in the database, aggregated database, and then workers are something that will run every week, right? So these can be some batch jobs or whatever. So these are going to fetch the data from the aggregated database, and then these workers will update your try database on weekly basis. Every week your workers will fetch the data from aggregated database and then update your try database. And you also store your weekly snapshot of the database in your try cache, so you do not need to make the so whenever new search queries are being searched, you just return those from the cache for faster response instead of sending those queries to your database. Okay. Okay, that's the thing. Next is so you have these analytics logs, and then like this, you store this here, and we also discussed the aggregated data, workers, try cache. One more thing you need to think, you need to look at here, that this is your scalable system, right? So these aggregators will also have some load balancer somewhere here, and then you will have these aggregators. These will be distributed, like you can have multiple aggregator servers, and then your aggregated data, like this data might have been used sharded. You might have used sharding for horizontal scaling. For workers, you also might have load balancers here and multiple workers. So this is just distributed. Your cache is distributed, your database is distributed. So whenever we are talking about scalable systems, you need to think that you just you assume that these are not single servers only, these are distributed. Okay. The next thing is
मैम हमारे सेशन का टाइम है
okay, I think so. Okay, and we can end the session for today and we can discuss the rest of the things tomorrow. Yeah. Any questions anyone have, then we can end the session. Yes, Afan.
मैम ये बताएं कि आपके जो है ना ये यूआरएल है ना
Hmm.
जो आपने ब्लॉग खोला हुआ है ये तो
Hmm.
अनलॉक्ड है। मैंने सर्च किया था तो मुझे लॉक्ड मिला था ना मैंने जब लॉगिन किया।
Hmm.
सो ये किस तरह मतलब आपने सब्सक्रिप्शन ली हुई है इट्स।
अच्छा नहीं, अभी आप ना अभी मंथ पूरा फ्री इसका अवेलेबल है, 30th तक अवेलेबल है। 1 अप्रैल से ये अवेलेबल हुआ था, लाइक फर्स्ट मंथ, मतलब ये पूरा मंथ फ्री था इसका। सब्सक्रिप्शन नहीं मैंने ली थी। तो ये 1 मंथ के लिए ना अभी बाइट बाइट गो पे फ्री है। यू कैन जस्ट एक्सेस इट, यू डो नॉट नीड टू एंटर योर कार्ड डिटेल्स और एनीथिंग। But what I have done is like I have also stored everything, like all of these HTML pages on my uh, I have just stored all of these here just to make sure that after 1 month is ended, I can still access these pages. So you can just log in और वहाँ से आप चाहे जब log in करेंगे तो you will be able to see all of these courses there.
ओके ओके
But ये सिर्फ
ठीक है।
1 मई से पहले पहले तक है। 1 मई के बाद these will be locked again because फिर आपको सब्सक्रिप्शन परचेज करनी पड़ेगी।
इसमें लोकेशन का तो मसला नहीं है लाइक वीपीएन तो मुझे
ओह
कनेक्ट
यस
कर।
यस यस, आई थिंक लोकेशन मैंने शायद यूएसए से एक्सेप्ट, हाँ हो सकता है। आप अभी पाकिस्तान में हैं।
जी जी
हाँ ये हो सकती है पॉसिबिलिटी। Okay, I can also share the downloaded pages as well. Like I have just
सही।
downloaded all of these. तो मुझे अब्दुल रहमान, लाइक हम इसको कहीं शेयर करके डाल सकते हैं so that students can, I don't know where
यस
we put
यस
these.
मैम इनको हम गूगल शीट्स के ऊपर जो आपका ये वाला फोल्डर है ना
हम्म।
आप इसको सीधा गूगल ड्राइव के ऊपर अपलोड कर सकती हैं
हाँ
तो
सही।
वो फिर शेयरेबल हो जाए
चलो ठीक है, ओके। All right, thank you everyone for joining.